Hello, welcome to Plutus Experience number 7. If it's your first time here, the link for the first video in this series is in the description. Please subscribe and tick the bell to receive notifications on new release. If you're following us so far, please leave a comment below. Aff. Aff is used to represent asynchronous effects, similar to proms, but with more features. So the computation may either error with an exception or produce a result of type E. This is pretty similar to effects, but with this added feature of being asynchronous. So what is being asynchronous means in computation? It means that we're not waiting for some feedback around the next line of your code. So that is an asynchronous computation. So imagine that we are like reading for some input from the user. If you have a synchronous computation, your program is gonna pause until the user have fulfilled the required data, and then we return to process the commands and the language, the line of your code as soon as the user have put the field there, for example. In a synchronous computation scenario, could, for example, while we are waiting for the user input, you could do something else, like pop-up user, hey user, fulfill the input. I am waiting here. Maybe you could like do a request, do some logging, do anything else while we're waiting for the user input. And in the JavaScript world, we normally do that with callbacks. That's one way to do that. And that is also another way to handle async code with wait async and proms. That's why it has here these proms that correspond to this aff on the PureScript. Okay, PureScript has also native proms, a data type that represents proms on the JavaScript side, but the aff is more. It has more features. So aff is like proms with more, you know. So it has more features. This is the type signature of aff. It's the same as effect. Okay. And to launch an aff, we use this launch aff underline, and the type signature is that. So for all E, it takes an aff having that E and returns an effect E unit. This is normally the function we use everywhere with aff types. So here's an example. In this example, let's see the main function here. We're logging the console. So this is the effect unit as before. We're logging the console. This is the effect computation. So we're producing some side effects on the world, okay, which is the console log. And here we are launching an aff, which is a synchronous computation, and we are using the aff monad. So aff, you're gonna see this aff has instance for the same thing as effect. It has instance for functor, for apply, applicative, bind, and finally monad. So you can do the same thing we do with effect. So we can use do notation like here, and we can like use the fetch function from a library called fetch. And we can, for example, request on this URL. We can request HTTP request, wait on the result of that request, and we wait that concept of waiting on something on aff is actually doing the extraction of the value. So when you extract the value of the monad, actually the computation has been fulfilled. So it has been produced the result. So in this case, the result is a record, and we extract the text attribute, the text labeled attribute on that record. And it happens that this attribute here in this record is also an sync computation. If you look at the type of text, is also gonna be another aff. So we wait on that aff, which is another async computation. We wait on this resolution, by doing the extraction of user ID. So we extracted the user ID from that text because an aff has also an instance for monad effect. Remember monad effect? We can lift effect inside of the monad. So when we receive this user ID, I'm gonna show in the console the user ID by lifting in the effects monad. And here is another parallel async computation. So we produce a new aff here. And remember, the launch aff returns an effect unit, right? So it matches this effect unit here. So we pass a new aff and we lift from effect. So we log other aff start and we wait using that delay function. So we have a function to wait for time and we wait for 1 second here in this case. And then we're gonna log using the lift effect the other aff done. So we kind of simulate another async computation using this delay function. And finally, we log program finish before async step. And notice that this is important because I'm showing that this log here is going to show before this and this to show you that the aff is going to run after the main function because this is a sync computation. So look here, we have the first log. This is an effect computation right here. Effect monad context. Okay, this is normal. We are expecting that. Then we have the other aff first. Pretty nice. So we have this other aff start program now. Before this aff finish before async stuff. So we have now the program being finished here, and in background we have the both aff running in parallel. So we have the first aff that has been already started here. And finally, we have the user ID being printed here. So after the main function finished, we have this user ID being printed here. After all that, we have the other parallel computation being done here. And there's no guarantee here of other. I mean, because I'm running this here in different computations of this effective unity, there is no guarantee that this thing is gonna happen and before that, and that's gonna happen before that, and even beyond that, like there's no guarantee that this final thing is gonna happen before or after this another aff thing. Okay, the guarantee that we have is that whatever we pass inside of this aff, like here, this every computation we do this inside this aff is gonna wait on the previous computation. So for example, we cannot run this lift effect passing this log show user ID while we don't have until we have the text, because we need the text to extract the user ID. And the same happened here. We cannot have access to the response of the fat while the fat has not been finished. So we need to wait there. So that's how we build this kind of layered dependence on a sync computation. And this is really where aff brights. I mean, using different monads for sync computations and async computations, and using monad to do that stuff, to interdependence, really improve code reading. You see that it's really nice to read that way, and you are not using like callback. No, there's this phrase we normally use when doing, for example, we are coming from Node.js JavaScript. We're pretty familiar with this callback hell concept, which is just passing callback functions to every function. So whatever is implement that library, for example, it receives this function and call that function when something happens. So this creates this cascade of, callback functions, which is really hard to read, and we don't have that using aff, which is really nice. So this is the aff instance. So as I said, beyond functor, apply, applicative, bind, and monad, we have monad throw. So we can throw errors inside of monad like we're doing effects. Also monad error, we can catch for errors. You can listen for errors and react for errors when it happens. And it also has monad effect. As we saw before in the last slide, we can lift effect in that MonadAff. And also we have MonadAff type class, which is the same thing as monad effect. Allows we to lift from aff in our custom monad. For example, contract we are building before. If we're like in that contract monad, I would like to have a synchronous computation beyond synchronous effect. I could use this MonadAff to do that. And this is the type signature. Links here. So UtxOs reference monad effect and UtxOs reference aff. Also, like before, I really recommend you to go there, read everything, try exercise to practice that, because we're gonna use that a lot in the next slides and the next exercise and modules.